My name is Dhruv Desai, and in this video I'm going to illustrate the use of total internal reflection to solve a problem. This problem was asked in the IIT exam. Okay, so the problem is, it goes like this. So I have a tank whose dimensions are, so there we go, this is my tank, right? This is my tank, and its dimensions are given 20 meters into 15 meters. That's a huge one. And it's filled with water. I have water all over here. There is my water. And now the question says that I have a bulb which is placed 2√7 meters beneath the surface of water. So if I assume this as the surface of water, then my bulb would be placed somewhere here, and this distance would be 2√7 meters from the surface, right? Now now the question says that I am supposed to find out the area from which the bulb from which the light rays which are emerging from the bulb, they could be seen outside the water. Now at a first look, this question looks a bit weird, because one might think that we could see it from any angle and we could see the light emerging from the bulb, but it is not so in case of total internal reflection. Now I'm not drawing the tank again, it's just this water surface and the bulb here. To illustrate, now let's say I have this is the area through which the bulb could be seen. So how would I determine this area? Like for this we need to use the concept of total internal reflection, right? And let me explain the concept of total internal reflection in brief. Now let me say that this is a medium, and this is a boundary which is separating two media. Let's say this is medium 2, this is medium 1, and medium 2 is optically denser than medium 1. So basically, when a light ray, let's say this is my normal, and when a light ray strikes at some angle, it bends away from the normal because it's denser, right? Now I have another light ray like this, it bends away like this. At a stage, at a particular angle which is known as critical angle, the light ray would pass along the surface, right? And at any angle greater than the critical angle, the light ray would be totally reflected back into the medium. So this phenomenon is known as total internal reflection, right? So let's get back to the question. So the question says find out the area. Now obviously, if the bulb is to be seen in this area, then here at this point, if a light ray coming from here at this point, it has to be reflected along the boundary. If it goes up, it's obvious, then the bulb could be seen from a distance, like the bulb could be seen from this point or this point as well, right? So this point, I mean, when I draw a normal through here, this angle should be the critical angle, right? Now let's suppose this is the center of that circular area which the light from the bulb coming out encloses, right? I'll extend this line, and obviously from the geometry of figure, this angle is also equal to C, right? Now basically, since this is equal to C, this is equal to C, let's suppose that C is my critical angle. Critical angle means beyond this, if a light ray strikes from the bulb strikes somewhere here, it will be totally reflected back. It's only in this part of the water that the light ray goes up, and then it could be refracted out of the water. So you could see the bulb only from this particular area, right? Now let's try to solve this problem. They say that this distance is 2√7 meters, and the radius of this is, let's suppose that the radius is r, radius of that circular area be r. So obviously from the figure we could figure out that tan c is equal to r over 2√7, right? Now how do you find the value of tan c? Because in order to find the area, you need to find the value of the radius r, and in order to find the value of the radius r, you need to find the value of c, or in short tan c. So how do you find? You could also write tan c as 1 by root of cosec squared C minus 1. Okay, one might be thinking as to how do you derive this formula. Actually, you must be, in case you remember trigo identities, then this formula, root of cosec squared minus 1 is equal to cot squared. So this term below is cot squared, and root of that will be equal to cot c. So 1 by cot c is obviously tan c, right? So I could write it in this form. Now, from Snell's law of reflection, what's the Snell's law? It says that the refractive index of the first medium with respect to second, second medium with respect to first, it's obviously equal to the ratio of angle of incidence upon angle of reflection. Now, it's obvious. If I take my first medium as there, then that will be this thing will be the refractive index of the second medium. So there we go. Here is my refractive index of second medium. What's my angle? It's a critical angle, and at the critical angle this ray emerges parallel to the boundary, right? So my R is equal to 90 degrees. So what sine 90 equals to? 1, right? So in short, actually there's my mistake. It's the refractive index of the first medium with respect to second. So actually it will be 1 by n, right? This is the refractive index of second medium. So in short, the refractive index of this medium would be equal to 1 over sine c. That's my formula, right? Now in this, I'll substitute what's the value of, so basically n is equal to cosec c. Now I'll substitute the value of cosec c for n. So what would my tan c be equal to? That would be equal to 1 by root n squared minus 1. Now for water, n is equal to 4 over 3. So what would my tan c be equal to? Tan c would be equal to 1 by root of 4 by 3 whole squared, right, minus 1. So what would that be equal to? My tan c, let me write it here so that it becomes more clear. The value of my tan c would be something around 3 over root 7. I substitute the value of tan c in this formula, right, and I'll get the value of R as 6 meters, right? I could find out the area. What is that equal to? Area is equal to pi into R squared, which is equal to pi into 6 squared, which is equal to 36 pi meters squared. So basically this is the effective area through which one could see the bulb, right? Now this is the practical application of total internal reflection, and at first look this might sound a bit weird or quite awkward, but when you apply logic, this problem could be easily cracked. So what I wish to emphasize here is not the fact that this is something which is very tough to analyze, but how to apply such kind of problems in situations in real life, because that's what matters.